So we're going to talk a little bit more now about what makes atoms different from each other. And so we're going to start out by talking about atomic number and mass number. So atoms of the different elements like hydrogen or nitrogen or oxygen are going to differ in the amount of subatomic particles that they're going to have. In particular, kind of the defining feature of an atom is its atomic number. And the atomic number tells us the amount of protons. So that's why it's in fact called the atomic number, because the number of protons really defines the atom. So let me catch up here in my writing. The atomic number is equal to the proton number. And again, this is characteristic of a particular atom. So hydrogen, no matter what's going on with that hydrogen atom, it always has one proton, or it always has an atomic number of 1. Whereas nitrogen, we were talking about, has 7 protons. It always has an atomic number of 7. So in a neutral atom, we said earlier that the number of protons is equal to the number of electrons. But remember, the caveat there is that it has to be a neutral atom. Okay, so that will get you to a net charge of 0. Okay, the other number here is the mass number. And the mass number is an approximation of the weight or mass of the atom. It's equal to the number of protons plus the number of neutrons. So notice that the mass number is really the amount of subatomic particles except for the electrons. So why can I ignore the electrons? Well, electrons are so tiny compared to protons and neutrons that if I just want to approximate the mass, I don't even need to worry about electrons, okay? But this mass number also becomes a nice way to figure out the number of protons and neutrons, because notice that if I have the mass number, so let me just make one up here. If I have the mass number, that's 36, and I know the proton number, which remember is my atomic number. So again, just throwing out some numbers here. I have no idea if these are any real element or atom. Then my neutron number is x, okay? And we really don't have to do any fancy algebra to know that x would have to be 10, or rather 20. Whoops. 20 plus 16 would give us 36. So that's how I would know the number of neutrons. So how might this appear on an exam? Well, here's a practice question right here. If an atom of iron has an atomic number of 26 and a mass number of 56, how many protons, neutrons, and electrons are there? So again, my atomic number tells me that the number of protons is 26. And again, if it's neutral, then that also tells me that there must be 26 electrons. In order to figure out my neutrons, I know that my neutron number is going to be equal to my mass number minus my proton number. So that's just a rearrangement of that equation. So my neutrons in this case are equal to, 56 minus my number of protons, 26. So there must be 30 neutrons in this atom of iron. So that's how you do the math for a problem like this. Okay, so atoms of the same element can also be different still. So let me give you maybe an example here, sorry. If I have hydrogen, if I'm talking about a hydrogen atom, sorry, I'm having trouble with my pen here, let me get it going. If I have a hydrogen atom, I can have a version of it that is that has 1 neutron, or I can have a version of it that has 2 neutrons. So the atomic number would be exactly the same. They both have 1 proton. Okay. They're both still hydrogen, because as long as they have 1 proton, it must be hydrogen, because that's the defining feature of the atom. But I can differ in my number of neutrons. This is what's called isotopes. Isotopes differ in their neutron number, and we often designate them as, this would be the 2 isotope of hydrogen. This would be the 3 isotope of hydrogen. So this number is the mass number. So isotopes are often designated through their mass number, and probably you've seen this before or more familiar with this in carbon. So carbon-12 is the isotope of carbon that has 6 protons and 6 neutrons for a mass of 12. Whereas carbon-14 is a different isotope of carbon. It's still carbon because it's got 6 protons, but it has 8 neutrons, and that gives it a mass number of 14. If you looked on the periodic table for carbon, you'd see something that looks something like, and I'm just sort of, making this up. I don't know the periodic table off the top of my head, but you'd see a number that's like 12.0 something something something. And that's because the mass that's given for the atom on the periodic table is actually a weighted average. And so, the main thing that's interesting about this is whatever number it's closest to tells you that it's the most common isotope. So the amount on the periodic table is 12.013. That's telling you that carbon-12 is the most common carbon on Earth. Carbon-14 is making this number be a little bit higher than 12, but there's so little of it that it doesn't actually contribute that much to the weighted average for carbon on Earth. Okay, so another way that atoms can differ from each other is in their charge. So I was using the example of hydrogen earlier, so I'll kind of stick to hydrogen for simplicity. So we can have a hydrogen that has 1 proton, 1 neutron, like we were saying earlier, and 1 electron. And this atom of hydrogen would have no charge. However, I can also have hydrogen with a positive charge, and this would be a hydrogen ion. Okay, how do I get to having a positive charge? So let me show you. It still has 1 proton, because remember that's the defining feature of being hydrogen. Still has 1 neutron, so this has a mass number of 2, but in this case it has 0 electrons. So now if I look at my charge balance, I have 1 positive charge, 0 negative charges, so I have a +1 charge. Okay, how would I create a negative charge in an atom? So let me just, I'll just make an atom because I can't think of one off the top of my head, but I'll just give an atom that has 16 protons and 17 neutrons, and the neutral version of it would have 16 electrons. Okay, that would make it neutral. We want to create a negative charge, so a negative ion of X. So it still has 16 protons, 17 neutrons, that's unchanged. But in order to get to a negative charge, I have extra electrons. So notice I can't change the proton number because the proton number is the defining feature of the atom. Okay, so proton number doesn't change. We get charges by having more or less electrons. In this case, I'd have 16 positive charges, 17 negative charges. That would get me to a -1 charge. Okay. All right. Last note here, a little bit not quite related, just because it doesn't fit in anywhere else, is how we measure atom quantities. So you can measure elements in moles, or sorry, in grams, just like we measure anything else. So let me get my pen up here, sorry. So we can use grams. And so I could say, well, I have 12 grams of carbon. Okay, that's one way that we measure things. But when we're dealing with atoms, for various reasons that we don't really get into in this class, it's often useful to measure number of carbon atoms rather than how much they weigh. And the best analogy I can give you for comparing grams versus number of carbon atoms is to think about like noodles at the store. You can buy a pound of noodles. That's a mass of noodles. Okay, that's the weight. Or you could potentially, instead of weighing out those noodles, you could count out 1,000 noodles. You say, I want 1,000 spaghetti noodles, rather than saying, I want a pound of spaghetti noodles. And so in science, sometimes we want to weight like grams, but many other times we want to count out exactly, for example, 1,000 carbon atoms. In order to do this, we actually use a unit called the mole, and that's represented here. Okay, So a mole of any element contains a number of atoms, and that number is 6.022 times 10 to the 23rd. Now that number is also using scientific notation, so let me take a moment here and write out what this number looks like. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So let me make sure I counted my zeros right here. 3, oops. Okay, if I were to write that number out in longhand, it would look like this. And obviously that's a nuisance to write out. It took me a long time to do it. And so instead we use scientific notation to write out very, very large numbers. We'll also see later on scientific notation to write really small numbers. So notice this negative sign. This makes this a really small number. So that number would actually be this written out. So notice it's a really, really small number. So that negative sign means it's a really small number. So that's scientific notation for those of you who are not familiar with it. So coming back to the mole means that I have a lot, 6.02 times 10 to the 23rd atoms of carbon in my example. This number is also known as Avogadro's number, obviously named after somebody. So again, I just want to reiterate that in our class, all we really need to know about this is that we're going to see it as a measurement at various times throughout the semester. It's counting atoms rather than weighing them. And just to give you sort of a conceptual understanding, again, if I took, which of these has more atoms, 3 moles of magnesium or 3 moles of calcium? So let me illustrate for you what this would look like. So I want to know how many atoms I have if I have 3 moles of magnesium. Well, that would be 3 times 6 times 10 to the 23rd atoms of magnesium. And the question is, how is that different from 3 moles of calcium? Well, 3 moles times that same number, whoops, and you can see that these would actually be equal to each other. Are these going to weigh the same? No, they're not going to weigh the same, but they're going to have the same number of atoms. So again, coming back to my noodle analogy, this might be spaghetti, and I might count out 1,000 pieces of spaghetti. And this might be macaroni, and I might count out 1,000 pieces of macaroni. So there's the same number of noodles, but this would actually weigh more. So it's just a different way of measuring atoms than weight. All right, so that wraps up this section.